In this video, I'll be solving first part of the third problem of UPSC Civil Services Mains 2017 Statistics Paper 1. So X1 is the time that a customer takes from getting on line at a service desk in the bank to completion of a service, and X2 is the time to wait in a line before reaching the service desk. And the joint probability density function is given by f of x1 comma x2 as e to the power of minus x1 when 0 less than or equal to x2 less than x1 less than infinity. And let y1 is x1 plus x2 and y2 is x1 minus x2. We need to find the joint probability density function of y1 and y2, and we also need to check whether this y1 and y2 are independently distributed or not. So first, like, if we consider the joint PDF of this x1 comma x2 with 0 less than or equal to x2 less than or equal to x1 less than infinity. So that is f of x1 comma x2 of x1 x2 is e to the power of minus x1, where 0 less than or equal to x2 less than x1 less than infinity and 0 otherwise. So if I define the transformations, y1 as x1 plus x2 and y2 as x1 minus x2. So then, like, x1 is nothing but y1 plus y2 by 2 and x2 is nothing but y1 minus y2 by 2. So if I compute the Jacobian here, so dou x1 x2 divided by dou y1 y2, so that is half. So dou x1 by dou y1, that is half, and dou x2 by dou y1, that is also half, and then like 1 by 2 and minus 1 by 2, which is nothing but minus 1 by 4 minus 1 by 4, which is minus 1 by 2. So 0 less than or equal to x2 less than or equal to x1 less than infinity. So that means x2 is greater than or equal to 0. That means y1 minus y2 by 2 is greater than or equal to 0. That means y1 is greater than or equal to y2. And x1 is greater than or equal to x2. That means y2 is greater than or equal to 0. So that means y1 is also greater than or equal to 0. So therefore the region would be something like this: y1 comma y2. y2 is greater than or equal to 0. y1 is greater than or equal to y2. And y1 is less than infinity. So that's our support here for the domain. It's a sort of a triangular region. So fy1 y2, like for this domain, would be fx1 x2, the joint PDF, x1 in terms of y1 y2, comma x2 in terms of y1 y2, into the Jacobian, or the determinant of the Jacobian, which is e to the power of minus x1, that's the joint PDF, into half. Now x1 in terms of y1 and y2 would be e to the power minus of y1 plus y2 by 2 into half we have. So that would be our joint density of y1 and y2. So half into e to the power, or exponent of minus of y1 plus y2 by 2, where y1 is greater than or equal to, y2 is greater than or equal to 0, and y1 is greater than or equal to y2, and 0 otherwise. So now, like, we can find the marginal density of this y2. So the marginal of this y2, so basically we need to integrate this from y1, this joint PDF, from y1 till infinity. So half times e to the power minus of y1 plus y2 by 2 dy1. So we can take this e to the power minus y1 by 2 out. So y2 to infinity, sorry, this is, we're doing it on y1. So y1 is going from y2 to infinity. So y2 to infinity, e to the power of minus y1 by 2 dy1, which is half times e to the power of minus y1 by 2. So the integral is 2 times e to the power minus y1 by 2 from y2 to infinity. So that is nothing but half into e to the power minus y2 by 2. Sorry, here y2 by 2 will be outside. y2 by 2 into, this is going from y2 to infinity, that is 2 times e to the power minus y2 by 2. So that is nothing but half into 2 into e to the power minus y2 by 2 plus y2 by 2. So therefore this marginal density would be e to the power of minus y2, where y2 is greater than or equal to 0. So that means y2 is following exponential distribution with parameter 1. So fy2 of y2 would be e to the power of minus y2, where y2 is greater than or equal to 0. In the same way, fy1 of y1 would be, so y2 is going from 0 to y1, so half into e to the power of minus of y1 plus y2 by 2 d by 2, which is half times e to the power minus y1 by 2 integral 0 to y1 e to the power minus y2 by 2 d by 2, which is 1 by 2 into e to the power of minus y1 by 2 into again like 2 times e to the power minus y2 by 2. This time it is going from 0 to y1. So which is nothing but half times e to the power minus y1 by 2. So that would be 2 times e to the power minus y1 by 2 minus 2. So that is nothing but e to the power minus y1 by 2 into e to the power minus y1, sorry, here minus also will be there. So therefore this will go from 0 to y1. So that means this thing will get inverted, like minus of this thing. So we'll get minus here and plus here. So therefore 1 by 2 into 2 minus 2 into e to the power minus y1 by 2, which would be e to the power minus y1 by 2 into 1 minus e to the power minus 1 by 2. So that is the marginal density of y1. So marginal density of y2, we got it as e to the power minus y2 when y2 is greater than or equal to 0. Here y1 is greater than or equal to 0. So we can clearly see, like if we multiply those two, fy2 of y2, which is e to the power minus y2 into e to the power minus y1 by 2 into 1 minus e to the power minus y1 by 2. So this is not equals to half times of e to the power minus of y1 plus y2 by 2. So that means these two expressions, like we can clearly see, they are not equal. So therefore the joint does not factor as this product of this marginal distributions, and so therefore they are not independent. So y1 and y2 are dependent, we can say, because they are not independent. Or like we can also clearly see the domain there. So if we remember, like we got a triangular support, so y1 is greater than or equal to y2 we got. So that means these both are like dependent. So we can clearly see the variables are also dependent. So that's like another indication of the dependence. So we can clearly say y1 and y2 are not dependent, and the reason can be like, first reason can be like the joint PDF is not the product of marginal PDFs, and secondly, like we can also state that the supports are like dependent. So y1 is greater than or equal to y2. So that's another reason for the dependence. So therefore y1 and y2 are not independent, and we have also found this marginal density functions of this y1 and y2. So that's it for this video. We'll meet in the next video.